Welcome back. This is the fourth class of EC253C, and last time we had introduced 8085 microcontroller. It's one of the earliest, actually the earliest microcontroller introduced by Intel. I have already told you that it's an 8-bit microprocessor, and also at a, it can access a memory of 64 kilobytes that I had explained because it has got 16 bit wide address bus that can access to raise power 16 different memory locations. Let's continue with some of the other features of 8085 microcontroller. 8085 microprocessor, sorry. So 8-bit microprocessor, it's 8 bits with a maximum capability of accessing 64 kilobytes of memory. Also the actual IC I will be showing you the IC maybe in this class or maybe in the next class. It's 40 pin IC. There are 40 different pins, 40 pins, and it also works on 5 volts. Supply voltage is 5 volts. Supply voltage V supply is 5 volts. 5 volts. The maximum clock capability is 3 megahertz. The maximum speed of this microprocessor, 3 megahertz. It's a very old one, that's why only 3 megahertz. The speed of microprocessors and processors we have today, the speed runs in gigahertz. 3 megahertz. So these are the basic basic specifications associated with 8085 microcontroller. And also let me explain this 8-bit in a detail. Since it's an 8-bit microcontroller, it means it has an 8-bit word length. Meaning any operation that can be done on an 8-bit data, one thing. It also means the internal registers, most of the registers, and also the ALU, that will be 8 bits wide. ALU will be 8 bits wide, and most of the registers are also 8 bits wide. So with 8 bits we can actually have 256 different bit combinations. Ranging from 00000000, and then 00000001 up to 11111111. So there are 256 different bit combinations, and each of these bit patterns, 256 different bit patterns, and each of these bit patterns can be a possible instruction. So each of these bit patterns can be an instruction. So actually our 8085 microprocessor can have 256 different instructions. So our processor, our arithmetic logic unit of our processor, can actually execute 256 different instructions. But in reality, only 246 of these bit patterns are used for instructions. That means there are 246 different instructions. The instruction set of 8085 microprocessor has how many instructions? 246. The rest 10 bit patterns are unused. So 246 different instructions. What can these instructions be? These instructions can be something like this: move. It's a very basic instruction present in almost all the processors. Move. Move is actually a symbolic code or we call it mnemonic. It has some function. There might be a particular opcode that is associated with move. For example, a particular bit pattern, maybe for example 0110 1110, particular bit pattern associated with move. What does move does? Move actually copies data from one location to another. For example, I can write move. What does this move do? This it moves data or copies data, moves data from one location to another. And what are these locations? What are these possible locations? They may be registers. So these locations between which our move instruction moves data, these locations can be internal registers in the register array. These can be two internal registers, or this movement of data can be between memory and an internal register. So for example, I can write something like this: move R1 R2. For example, I have named my internal registers, the internal registers present inside a microprocessor, this register array. The internal registers present in this register array, I have named them, or Intel has named them as R1, R2, R3 and so on. So we can use this instruction move to actually move data from R2 to R1. In fact, it actually copies the data. It will copy the data from R2 to R1. Or I can also write as move R3 R2. In this case, it will move data from R2 to R3. And in reality, these are two different instructions. The instruction is same, moving the data, copying the data, but the operands, where to find the operands, are different. In the first case, the movement has to be from R2 to R1, and in the second case, movement has to be from R2 to R3. Similarly, we can have we can be moving data from other registers to some other register, or from to memory to registers, or from register to memory, some particular memory location. Like I can say move R3 46. So any data at memory location 46 will be moved to register 3 inside the processor. So basically this is the same instruction, move, but the operands are different. So out of 246 instructions, most of them are same. The operation is same, but where to find the data, the operands, that is different. So actually 246 different instructions, they only translate to 74 unique instructions. So we have 74 unique instructions inside 8085, and depending upon the data they operate on, they translate to 246 different instructions, and each instruction can have different types of data, different types of operands, different types of ways how to find the data it wants to operate on. And remember, each of these instructions, move R1 R2, it will have a different opcode, a different bit pattern. Maybe it will be 1001, maybe 1101, but move R3 R2 will have a different bit pattern. Maybe it will be 1001 1110, and move R346 will have different bit pattern. Maybe it will be 1001 0011. So our the ALU, arithmetic logic unit, inside 8085 microprocessor is capable of actually executing 74 different instructions, and these instructions can be one I have mentioned here, move, which actually moves data, copies data from one location to another. These can also be instruction like add, that adds to data, or subtract, or incrementing a particular register or a particular memory location, decrement, and or there are other instructions also. We may be going into detail in subsequent lectures. 74 different unique instructions, and since their operands differ, these 74 unique instructions translate into 246 different bit patterns, and each bit pattern actually has a unique opcode, or has a unique mnemonic. Mnemonics are symbolic codes. Like this bit pattern may be move R346, another bit pattern may be randomly, I will say like this, 10000000. This opcode has a mnemonic that is add. There's a register inside our 8085 named as B. That means if my processor finds this number 10000000 inside its memory, it will actually add the contents of B. How exactly will that be done? We'll discuss that later. How it will add contents of B to what register and where to store the result, that's a separate question. But once we write add B, it actually gets translated to 10000000. This thing gets saved inside a processor, and when processor reads 10000000, it knows that I have to add contents of B to some other register and store results there. One more thing you should remember here, that machine language, or for that matter assembly language, because the only difference between machine language and assembly language is that we have represented these binary bit patterns using mnemonics. So machine language and also assembly language that are completely machine driven. For example, there might be an instruction that will be executed by 8085 microprocessor, but the same instruction, same opcode, same bit pattern, for example this bit pattern will translate to add inside 8085, but same bit pattern may translate to some other function, maybe to increment inside some other microprocessor, maybe 6800 Motorola 6800 microprocessor. So assembly language, or for that matter machine language, they are completely machine driven. Before writing a program, before writing these mnemonics, before writing opcodes, we must first check which opcodes, which mnemonics a particular microprocessor supports, and what exactly is the function of these what exactly is the function of these opcodes inside that microprocessor. Okay, so this was a brief overview of instruction set of 8085. We may be actually discussing most of these 74 instructions in subsequent classes. So let me now discuss one more thing. So far we have got the big picture of our microprocessor. We say that inside the microprocessor there are three main units. There's a timing and control unit, there is ALU, and there is there's a register array, different number of registers, and we have also discussed the function of these units briefly. So let me Let me today discuss the internal architecture of 8085 in a bit more detail. What exactly happens inside? So first of all, inside the microprocessor, we have our arithmetic and logic unit. Arithmetic logic unit, it's an 8-bit arithmetic logic unit. Remember, it will be accepting 8-bit data and output will also be 8-bit. There will be two inputs usually, because for most of the instructions or for many instructions we need data two data. For example, for addition we need 2 bytes to 8-bit data, and the output will be only one. So again, excuse my poor drawing skills. So let me call this ALU. This is 8 bits wide. Let this be my 8-bit internal data bus. These are wires which actually transfer data from one component to another component inside the processor. 8-bit internal data bus. So our arithmetic logic unit will be getting data from this. Eight-bit data. And after processing this data, it will put it back. This data may be coming from temporary registers or from the memory. For example, I need to add this data and then I will put this data back. Usually I put it on a special register, special internal register known as accumulator. I will discuss that later. Okay, and then we have the register array here. These are registers. Okay, fine. So registers are actually of two types. Inside the microprocessor there are two types of registers. The difference is in the functionality. One type of registers we call as general purpose registers. They do some general jobs like holding data temporary. And then there are some special registers. We call them special function registers, SFRs. Special function registers. We'll be discussing those also. What exactly are special function registers and general purpose registers. So first of all, I have accumulator. Accumulator, it's the name of a register. Accumulator, and it's an 8-bit register. I have flags. My flag, sorry, flags. Again an 8-bit register. These are special registers, special function. They have a special function. We'll be discussing that special function later. Accumulator and flag. Then we have 6 general purpose registers. They are also 8-bit. We have register B, C, register D, register E, B, C, D, E. We don't have F and G. We have H and L. All are 8-bit registers, every one of them. Then we have 2 more special function registers, and they are 16-bit. We have stack pointer. It's a 16-bit register. And we also have program counter. It's also a 16-bit register. And then there is another 16-bit register. We call it increment / decrement address latch. It's also a 16-bit register. So, and these registers, every one of them, they are also connected with this internal 8-bit address, 8-bit data bus. So far so good. We have an arithmetic logic unit that's 8 bits wide. We get 2 inputs, and then after every operation, arithmetic logic unit gives an 8-bit output that's fed back to the data bus, internal data bus. Apart from these 2 things, we have timing and control unit. Timing and control unit. There are 2 special registers that are associated with this timing and control unit. Both of them are 8 bits, and they are known as instruction register. We call it instruction register, 8 bits. And then we have instruction decoder. Okay, this is it. And then we have, this is our processor, the internal details of our processor. Then also we have our memory that needs to be connected to the processor for functioning, because program is in the memory only. So this is our memory. So we have there are 2 lines that connect with the memory. One is address bus, that is 16 bits long, and then we have data bus, that's 8 bits long. That means we have 16 lines, 16 different lines that are used for address, and we have also 8 other lines that are used for data. This address bus and data bus connects our processor and memory. This address bus is unidirectional. That is, their data only comes from processor, address only comes from processor to the memory. But data bus is bidirectional. Data can be written to the memory or read from the memory. In fact, in reality, there are not two. These are not 2 separate buses. That means we don't have separate 24 lines, but we have only 16 lines. 1 2 3 4 5 6 and up to 7 8, 9, 10, 11, 12, 13, 14, 15, 16. On one side of these 16 lines we have our processor, microprocessor, and on another side we have our memory. And these 16 lines are used for address. Whenever microprocessor wants to read from a particular address of the memory, it puts the address on these 16 lines, and sends it to the memory. A particular address is selected here, and then the data needs to be sent back, and using the first 8 lines, 1 2 3 4 5 6 7 8, using the first 8 lines, this data is sent back. That means these 16 lines, 8 of them are used both for address and also for data. So I will be drawing them accordingly. Address is generated in this register array, and then this address has 2 parts. We call this part as AD0, AD7 to AD0, address and data bits 0 to 7, 8 different bits, and then the separate part A15 to A8. This is known as address buffer, that temporarily holds actually upper byte of the address, because address has 2 bytes, lower 8 bits, and upper 8 bits, lower byte and upper byte. And this is known as data buffer, because this holds both the things, lower part of the data and also lower part of the address and also data. And here we have, this will be unidirectional, but this one will be bidirectional. This actually will be putting back data on the 8-bit internal data bus. So this is the complete diagram, but for now it is complete. There are some inputs that are going inside the timing and control unit, and also some outputs out from the timing and control unit, like clock. We have a oscillator that is always connected to the processor, that is actually connected to the timing and control unit. External oscillator that actually creates those timing signals. And there are other things, other control signals that come out of this control unit. Let's not discuss those for a while. Let's again focus on this thing. What we have got here now, we have our processor. This is our processor. And our processor is communicating with memory. This is A15 to A8, and this is AD7 to AD0. That means there are 16 different lines, 8 here and 8 here, that communicate with memory. 16 lines are used for address, and only these 8 lines are used for data. So it communicates with memory, it gives memory a particular address, and then reads the data from that address. Data temporarily gets stored in data buffer, and then it's put on this 8-bit internal data bus to be stored in one of these, temporarily stored in one of these internal registers. So ALU is here, and inside this processor we have 3 main parts. We have our ALU, that's here, and we have our timing and control unit, that's here, and then we have register arrays. And inside register arrays we have 2 types of registers. We have special function register, and they have some special name like accumulator, flag, accumulator, flag, we have SP stack pointer, we have PC program counter, increment, decrement, address latch, we have address buffer, we have data buffer, and then we have these general purpose registers. So again, let us go. Let's look at it from the outside. What exactly happens? First of all, we write a program, and that program, maybe we write in high level language, or we may write in assembly level language, but at the end of the day it actually gets translated into bit patterns, zeros and ones, and these zeros and ones are actually stored inside this memory, each byte starting from the memory location 0000. So maybe here is something 01101111, then in the next memory location we have some another bit pattern, and so on. Maybe for 50 different locations. Our program is only 50 instructions wide, instructions big. So what happens? Let me start with this program counter. What is this program counter? It's a special register, 16-bit register. What's the job of this program counter? This program counter actually holds the data of the instruction that needs to be executed, holds the data of the next instruction that needs to be executed. So at the start of the microprocessor, when we power on our microprocessor, in most of the microprocessors, this program counter, this is 16-bit wide, this will have a data of 0000, all zeros, 16 zeros. So maybe I am writing in hexadecimal, I will put an H here, hexadecimal, to make these things short. 0000 means all zeros. Program counter will have 0000. So what it will do, what our processor will do, whatever is there inside the program counter, that actually is the address of the first instruction that needs to be executed. So this number here 0000 inside program counter will be put here on this address bus 0000, and then two of the bytes will be put here 00, and 2 bytes here 00. So inside the memory, the first memory location which had this address 0000, next memory location will have 0001, and so on up to 1111 1111, and that is actually FFFF, last memory location if we have 64 kilobytes. So this memory location gets activated, and the number here, the bit pattern here 0110 1111 will be read by the microprocessor. It will be read by the microprocessor, and using this data buffer, then put on this 8-bit internal data bus and put directly inside this instruction register. That means this 0110, I will also write this in hex. 0110 is your 8 9 10 11 12, 8 9 10 1 2 4 8. So this is how much is this? This is 6F. So 6F will be written here, 6F. So what happened so far? Program counter has 0000. So 0000 memory location is activated. We have read the contents of 000 memory location, and that holds a particular bit pattern. That means a particular operation is associated with that bit pattern that gets read and is put inside instruction register. Of an instruction register provides this bit pattern 6F to instruction decoder, which actually decodes this instruction, what exactly this instruction means, and tells and actually transfers these contents to timing and control unit, so that it will initiate it will initiate a particular time control signals. So maybe this 6th step instruction was for add. So that very block of arithmetic logic unit will get activated. This instruction will also have information inside its bit pattern, where from we need to get the operands. Maybe we need to get operands from B and C, maybe, for example. So B and C registers, they will transfer whatever is in there to arithmetic logic unit. Arithmetic logic unit will add them and then store back this result in some another register. This is exactly what actually happens inside a processor. And after this instruction is fixed, program counter auto increments itself. It has the value 0000, it will get the value 0001 auto increment, and then puts the same on the address bus, and next memory location is read. That may be the bit pattern of another instruction. That instruction is put in the instruction register, decoded here, and necessary control signals are generated by the timing and control unit, and the instruction is executed. Similarly, all the instructions inside the memory are executed one by one by our processor. I think that's it for now.